Hey there, Calc 3 folks, back here with what is almost our last lecture. I think this is our second to last lecture in the study of vector calculus, where we are continuing to look at what we call the idea of a surface integral of a vector field, where we are going to spend some time with what is known as Stoke's theorem for circulation. All right. And what Stoke's theorem for circulation gives us is a way of calculating the circulation along the boundary of a surface S produced by some vector field F bar over which the surface is occurring, right, using what we call a surface integral calculation across this surface. All right? Yes, we are considering calculating what would have been that linear integration, right, for circulation that we saw back in the beginning of the chapter using techniques of surface integrals here at the end of the chapter, right? Where if we look particularly at Stoke's theorem, this is what Stoke's theorem says, showing this connection, right? Suppose S is a parametric surface with a distinct closed boundary described by curve C, all within three-dimensional space, all right? Occurring within a vector field F bar, right? In that space, the circulation of F bar along C, which we understand back in the beginning of the section of material, or back in the beginning of the chapter, was highlighted by this linear integral calculation of a vector field, taking the field and dotting it with tangentials to our curve C to determine how much the field was moving with the curve C, described by the direction of those tangentials. We're going to be looking at this calculation for circulation presented earlier in the chapter and approaching it with this calculation seen here, where this calculation is highlighting what we have as a result is a surface integral, this double integral over surface S that's happening with respect to the surface area of S, where now our integrand assumes this form seen here, where if you take note of that integrand, right, it is again this cross product of the del operator with our field. And if you take note, the del operator crossed with the field is the description of the curl of our field. That is the curl of the field. That is this. Let me think about this for just one moment. Okay, that just took a moment. What we have here is a vector, right, describing the curl of the field. When we take the del operator and cross it with our field function f, that does produce another vector, that vector known as the curl of f bar, right? That vector describing both the magnitude and direction of that curl, right? Dotted with, right, what would be the, we would think of here as vectors that are normal to our surface, right? If we dot the curl vectors on our surface with the vectors that are normal to our surface, what we are going to obtain in a surface integral calculation for that dot product is going to be the circulation of the field along the boundary of that surface. All right? And notice this is a, what do we say here? This would be a description of a surface integral over a vector field that we had seen in the previous section, right? In the previous section, what we had noted was we were calculating this particular dot product. We were taking the dot product of just f alone with n, and we had an approach for that did involve going into our description of region R in our calculation and having this all happen with some integral over the area of R, right? That integral calculation back in that case, right, being, what did we get for that? Let me just pull that up. Again, that is surface integrals of a field. That was calculated, yes, right, as we see here, right, back in those notes, it was more or less then going to just be the dot product of the field dotted with these two vectors, t bar of u, t bar of v, right? Where what we actually might do is go ahead and translate this over into our current set of notes, right? And say that what this is going to end up equaling is going to be this dot product, right? Seen here. Well, let me first of all, I can't go back there and undo that. Let me grab that here. Right? Remember, this was the quantity seen in here. Where, let me pause. All right, folks, I think back here, I think I have this how I want it so that this is hopefully a little clearer as opposed to just making this statement here. Because the idea is that we are going to take now this double integral where what we understand about this cross product for the del operator with f is that is the curl of our field f bar in three-dimensional space, right? Here, all the setup being in 3 dimensions, that is going to be the curl of f bar in its description. So we are going to approach this double integral for the curl of f bar dotted with n bar as we had done with surface integrals over vector fields in our surface flux calculation, and consider expressing that vector, that curl vector in terms of u and v, and dotting it with the cross product of t bar of u and t bar of v, where we translate our surface S parametrically into r bar of u comma v over region R, described in two-dimensional space by the parameters of u and v. All right? Where we end up seeing here that this linear integral calculation can be approached as the surface integral calculation involving what is the curl, right? And interpreting that curl, right, into a bit of what we think of as a flux calculation, this being this flux calculation from the previous section that involves the curl, right, into the methodology we had in the previous section for calculating that flux, which would be translating that curl in terms of the parameters u and v and dotting that with the cross product of t bar of u with t bar of v. T bar of u and t bar of v being these vectors of partials coming from our parametric description of the surface S. All right? So, there's a lot of steps in preparing up these calculations, folks, but it is, as we see here in the calculation, breaking down what could be a rather complex single integral calculation into what might be a rather simplistic double integral calculation when we are working with these bounded curves of C. All right, where in this particular case, we are going to again obtain the circulation on this curve C, where C is acting as a boundary on our surface S in three-dimensional space. And we're calculating the circulation on curve C of the vector field F bar using this double integral calculation seen here. All right, now, what you will notice is this looks a lot like, if we think about curl along F, this looks a lot like the case for, Green's theorem. If we took out this factor right here and just considered integrating across the curl of F bar, right, the integration across the curl of F bar over a two-dimensional region does tell us the circulation on the boundaries of that region. This is Stoke's theorem, where we are just scaling the result for Stoke's theorem by some sort of Jacobian multiplier as we translate our surface S into this two-dimensional region R, this surface S in 3 dimensions into this two-dimensional region of R seen here, or described here by our parameters U and V. All right? If we look at a particular example, I consider consider the circulation, right, of what would be the field F bar equal to y comma xz comma negative y along the curve C in two-dimensional space defined by the ellipse, or I really should say defined by the boundary of an ellipse given by x squared plus y squared over 4 equal to 1 in the plane of what we might say is two-dimensional space where z is equal to the value of 1. All right. What we have going on here, right, is a case for calculating the circulation along the boundary, the circulation of this field in 3 dimensions along this curve C, right? Where curve C is the boundary on some surface here in 3 dimensions, this surface being the ellipse defined by these values of x and y in the plane of R2, where z is held constant in 3 dimensions at the value of z equal to 1. All right? Now, this is a 3-dimensional consideration that is really happening over a 2-dimensional surface. And what you might be going back to and saying, Mr. Sexton, well, can't we just approach this with a little bit of Green's theorem that we saw previous in the section? And I would say, yes, you could, but what you're going to have difficulty doing is actually performing that integration. The integration is going to set itself up as a tricky, cumbersome integration. Whereas if we were to approach this now in the context of Stoke's theorem, where we consider approaching it using this surface integral calculation as opposed to this double integral calculation over region R that we saw developed in Green's theorem, right? It is going to become more of what we might say is a doable calculation here, right? Where to begin this calculation, right, I do take note in the plane z equal to 1, the surface S could actually be defined parametrically seen here, right? In terms of a parametric description of that surface, you will notice when z equals 1, right, the z component in this parametric description would be equivalent to 1, whereas our values of x and y in this parametric description of the surface can be expressed describing this elliptical shape if we were to use the arguments v cosine of u to describe our values of x and 2v sine of u to describe our values of y, where u and v themselves then occurred over values for u from 0 to 2 pi in our two-dimensional space, and values of v occurred over values from 0 to 1 in our two-dimensional space. Right? What you will notice is that these parameters for u and v, these parametric descriptions here, will lay out a surface in three-dimensional space here that is described by an elliptical shape in the plane where z is equal to 1. Right? What you will notice is if you substitute in here the argument v cosine of u, right? And if you substitute in the argument 2v sine of u into this statement here, and you simplify those statements, you will end up with v, You will end up with, v squared equal to the value of 1, right? You will end up with this description of the parameter v, right? That helps to describe how this plane or this elliptical surface is playing out, right? What I should really say here is that it's going to take some practice working with just defining parametric surfaces. So you want to make sure that you in the previous section of material are not only putting in the time calculating the surface integrals, but that you're also putting in some time attempting to understand different ways of defining a surface parametrically, right? This is a case that's very much analogous to defining a line in space that might, a curve in space that might be circular in a bit of a polar context, as opposed to trying to maintain a rectangular context. What we are doing here is approaching this calculation of this elliptical shape in the plane, in the description of this elliptical shape, not in the rectangular context, because that will bring about some complex descriptions as arguments of x and y, right? But in terms of the polar context, where we can see that u and v are going to be treated a lot like polar parameters, where u is going to be a lot like theta from 0 to 2 pi, and v is behaving as this radial measurement from 0 to 1, right? This polar region seen here, how we might understand it, right? This polar circle of radius 1 is being morphed into what we might say is this polar ellipse, describing this surface in three-dimensional space where z happens to equal 1, by converting our understanding of x and y in that space into these descriptions that are happening in the polar context. And where this comes from, folks, is again a lot of practice. There, a lot of practice with parametric surfaces, and it begins with the analogous of being able to understand how to define curves parametrically with vector valued functions involving just single values of t, parameter t, right? This is now going to incorporate two parameters into that description. And how could we use two parameters to start talking about location in 2 and 3-dimensional space for these surfaces, right? And we do see that this is the case for this surface seen here in this example, right? And what you've noticed in my notes is I've tried to do several examples of parametric surfaces to give you some different bits of notes to go with here, folks. But it is going to come down to a lot of practice, I will tell you, all right? Now, in the case of our vector field f bar equal to this field y comma xe comma negative y, what we are going to need in our calculation, as we have highlighted here, is we are going to need the curl of f bar in terms of u and v. And what we're going to form first of all is going to be that curl of f bar, right? This is going to be the curl of f bar in terms of x, y, and z forming here, right? Where if this is the curl of f bar in terms of x, y, and z, taking what? The vector f bar seen here in the third row of this determinant calculation, the second vector in our cross product, and crossing it with this del operator as the first vector in this cross product, right? If we go through that determinant calculation, that cross product calculation that's going to give us the curl of f bar in terms of x, y, and z, that will be this description seen here, right? Where now we're going to interpret that description in terms of u and v, where I know x in that description is described by v cosine u, y in that description is described by 2v sine u, and z is described in that description by the value of 1. And you will notice if I plug in z for 1 here, that will turn into 0. And if I plug in for the value of x seen here, v cosine u, that will turn into negative 1 minus v cosine u. So it will be negative v minus cosine u, 0, comma 0, would be the description of our curl in terms of u and v. And similarly, what we might do is actually make that transformation here. Let's actually say this, implying the curl of f bar in terms of u comma v then is just equal to the vector, what do we say that was going to be? -1 minus v cosine u comma 0 comma 0, where I am coming into this curl description in terms of x, y, and z and replacing the x with v cosine u, this quantity here. Y is 0, so 0 doesn't get replaced with anything in that description, but z minus 1 gets replaced with a value of z equal to 1. So that turns into this description here. And that integration, right, that we would see here for this linear integral calculation of circulation over curve C, which is being approached as this surface integral calculation defined here, given above, will actually be calculated using this double integral calculation here involving the curl of f bar in terms of u and v and its dot product with the cross product of these two vectors t bar of u and t bar of v. All right, and let's highlight that as the integrand. We're now, to continue, right, we did point out that this is our surface description over this region of R, right? Where if we now consider taking the partials of this value r bar in terms of u and v, we can prepare these two vectors t bar of u and t bar of v, and that is what follows here. Right? Where for s bar, right, and r bar, as we've defined above, t bar of u and t bar of v will take on these respective quantities, just the partials of s expressed as r bar of u comma v for both u and v. Right? Here's the partial of that statement with respect to u. Here's the partial of that vector with respect to v. Further implying let me just double check. Let me get a further implying in here. Further implying, right, that then the cross product of these two vectors we're going to use up here in our calculation, right, is just going to be this vector crossed with this vector, right, and that would be this determinant calculation seen here. And if we calculate that cross product, that will yield the result 0, 0, negative 2v. And what negative 2v becomes, as again we've said, is going to be what we think of as this Jacobian multiplier that would be occurring back here in this Green's theorem calculation of the circulation over this elliptical region of R. The Jacobian multiplier that would be involved in translating what would be this polar circle in our description of R into that elliptical surface, right? That elliptical region defined here by S, right? Negative 2v, or really I should say this vector 0, 0, negative 2v is going to become, in a sense, this Jacobian multiplier happening here, right? Or the description thereof. If we then consider our calculation, right, what we've prepared, let's change it respectively. We did make this one small change in that calculation, right here, right? That will yield then over these boundaries of R, the bounds from 0 to 1 for dv, and the bounds 0 to 2 pi for du. Right. Where if we set up that, notice dot product calculation, the dot product of this was 0, 0, and 0 here. Right? That'll be 0 plus 0 plus 0 when we perform the dot product, which is just the result of 0. leaves us with this integration over this value of 0. This double integration over this value is 0, where what is the double integral over 0? Well, it is itself 0. All right. If we were to carry this out, that 0 being a constant multiplier, or that might being, again, we go back to the idea that what are we calculating in a double integral is a net volume trapped between the surface F and the xy plane, where here, or in this case, the UV plane, here that surface has a height of 0. So what's the volume? Well, it's nothing, right, in its calculation. It is going to give us a 0 in its value, right, in the end. So 0 is going to be the measurement of what we're describing as the circulation along this elliptical bound. This elliptical bound here, well, this elliptical surface along the boundary of this elliptical surface in three-dimensional space, right, produced by this field will be 0 in value. Now, to help understand that calculation again a little further, we might look at the illustration of this surface. And this surface, although is set up to exist in three-dimensional space, can also be viewed in 2 dimensions, right? So by just focusing on the plane in 3 dimensions where z is equal to 1, this would become the surface's description and the description of the field in that plane. Where if we look at the description of the surface and the description of the field in this plane, and we notice how that field is behaving in terms of causing this counterclockwise circulation around the boundary of this region, notice that circulation appears to be balanced. If we were to consider the curl at any point along this surface, that curl would have a rather balanced description. If we were to put a paddle wheel up here in this region and a paddle wheel in a similar location below the x-axis down here in this region, what you will notice is this paddle wheel would have a tendency to want to spin clockwise, whereas this paddle wheel, be careful there, would have a very similar description, but as we move, that would be clockwise, that would be clockwise. Whereas here, out here on these ends, you would see that the paddle wheel would have a tendency to want to spin counterclockwise, right, in either direction. And these counterclockwise spins seen in these regions of the space, right, will in effect be balanced with the spins in the clockwise direction seen here in the space. And in fact, as we move around the curve in a counterclockwise direction, we can notice the field is contributing here to the motion in that direction along this boundary over here. And it's contributing to the motion of the direction in this boundary here. But there is this location on the curve where it translates or transforms from contributing to it to when we move up into this region here, you can see up at the top of this ellipse, the field seems to be opposing that counterclockwise direction. And then it transforms back into helping it, contributing to it, and then translates back into an opposition against it. Where along this elliptical shape, the field is contributing over portions and it's inhibiting over portions that circulation. Contributing, inhibiting, contributing, inhibiting. So that amount of contribution must be being canceled with the amount of inhibition, right? That the field is producing, right? Giving us, in a sense, a balanced circulation calculation around the boundary that measures the value of 0 in the end. All right? Folks, again, what we are looking at here is making some connections between linear, double, and linear integrals and surface integrals, right? Where we are going to approach this, in the case of Stoke's theorem, the circulation along a curve that we're familiar with being a linear integral calculation using this surface integral calculation, which is itself just a variation of what we might say is Green's theorem, right? A Green's theorem calculation that happens out in a three-dimensional surface that is going to require a little scalar multiplication of that vector description for curl to bring that three-dimensional surface down to a two-dimensional understanding of a region R. All right? And then once we have that set up for what is Green's theorem in the context of R, we do have a method that we can go about calculating what could be a linear integral operation that is rather cumbersome and tedious and maybe even impossible in the context of a linear integral calculation. All right? If we consider trying to perform this calculation down below, right? The calculation along the boundaries of this elliptical curve in our field f bar here using a linear integral calculation, that would be, I think, something that would be a little on the cumbersome side, if not impossible. Whereas if we try to approach it with Green's theorem, we are also going to encounter that difficulty where to actually get through this calculation, now we see that through the method of Stoke's theorem, there is a way to perform this calculation in vectors calculus, treating this as a surface integral, right? And considering here that we're integrating across some specific surface, right, that exists out in three-dimensional space, and the respective setup for that surface integral operation being calculated in the context of how we approach surface integrals as this dot product of these two descriptions. The dot product of the vector or of our field description with this normal vector being translated into the dot product of this curl vector in terms of the parameters u and v, and how parameters u and v are transforming surface S into R. Right? The cross product of their partials with respect to u and v in that description of our surface in terms of our bar. Right? So again, folks, this is Stoke's theorem. It is kind of combining some previous ideas into an approach that happens in a more complex scenario to allow that calculation that we've seen in a simpler context to actually be what we might say doable in its calculation. All right? Again, that is Stoke's theorem, folks. With that said, I will end my video there. We do have one last lecture to come back to where we take this idea of surface integrals and we go 1 degree further into developing the divergence theorem, which is going to be looking at calculating the divergence within a solid, right? Using the divergence within a solid region of space to calculate what we say is the outward flux across the boundaries of that surface, right? Or across the boundaries of that solid, which is going to be itself a surface, right? So that's divergence theorem, and that is where we plan to end this semester. I will try to have that lecture up to you as soon as possible. I still have to write up those set of notes as of the time of the recording of this video. But as you can see, the ideas here, these last few ideas, there's not much being presented here. There's basically going to be just a couple of more theorems, right? Stoke's theorem and divergence theorem. That's it. That's what the sections are focusing in on. So they're heavy in material, but they're not heavy in content, folks. So they're heavy in theory, but they're not heavy in a lot of different ideas being presented. All right. So keep that all in mind here as we end the semester. And I'll have that video up for divergence theorem ASAP. I'll see you all next time.